Hello and good day. I hope you're having a wonderful day. Today we're going to talk about linear probability models. This is another section in econometrics. I hope you've already done the dummy variables one, the interactions with dummy variables, and now we're going to talk about LPMs. Welcome. So what are linear probability models? We're going to talk about those. When do we use them? We'll talk about some real life examples. And of course, along with that, we'll actually do something just like we've been doing. You can get your either coding skills or your R stuff already. And then we'll talk about the interpretation and conclusion. So my name is Dr. Shalini Gopalkrishnan. I'm a professor in data analytics in the Bay Area in United States of America near San Francisco. I'm excited to do this with Sidra AIPG, and I hope this has been useful for all of you. So we're going to talk about linear probability models. They're also called LPMs. LPMs, okay? So what are these models? Now let's say we are sitting and creating a regression model, but in which the outcome, the dependent or the response variable is a binary variable, a yes or a no, success or failure. It's not a continuous ratio one. Now, if you remember from your regression times, you need to have good ratio data to be able to do robust regression models. But there are times when you don't have that. And we can't say, oh, we don't have regression data, so therefore we should not be able to do this analysis. They're important. So whenever the outcome has a binary variable, that's when you actually sit down and use LPMs. But what about the inputs? The inputs can be continuous, they can be ratio, they can be dummy variables, they can be 1, 2, 10, as many as you feel like. So the big thing about LPMs are the outcome, the DV, the dependent variable, is a binary variable. They're also called LPMs, logistic models, binary regression models. Now, take a minute and think of some examples in econometrics. I'm going to give you about 2 minutes to sit down and think about this. I hope you've thought of some interesting ones. Let's see some. Examples of outcomes could be, are you approved for a house loan? Yes or no? That too. Did you have the disease? Yes and no. Could also be people will die from it. Yes and no. Could be from COVID, right? Maybe we have these underlying factors. Will people get COVID or not? Yes or no, 2 factors. Success or failure. Let's say in an econometrics model, we are trying to say, hey, we're going to implement a new policy. And, we want to know whether the policy was successful. It could be like, hey, maybe I shall start giving education for all people from ages 6 to 18. And then you want to see whether it's a success. And there are many factors, but maybe you just want to see if it's successful. That can also be a binary variable. So those are places where you can actually use them. Now think about the assumptions of regression. Normality of error term, not going to happen. Homoscedasticity. Why will homoscedasticity not happen? Because remember, you only have groups of 0 or groups of 1. So you'll obviously not have homoscedasticity. The Y estimates may probably be more. Now, the data obviously is going to be 0 or 1. But when you're estimating it, you could probably get 1.2 or negative something, because the model, the slopes could actually show you slightly different things. And therefore, these assumptions won't work. So what do? How do we solve these assumption issues? We solve it by using something called logit or probit models. And we also use heteroscedasticity robust standard errors instead of the normal standard deviation errors that we use. So logit and probit models are the ones that are used to solve these problems. We'll first talk about LPMs, and then we'll talk about logit and probit models. LPMs are used a lot. They're nice and useful, but and they're useful because the interpretation is easier than if we had used a logit or probit, and that's why it's very popular with econometricians. Like we said, there are issues that we talked about earlier, so it's okay to start doing LPMs, but traditionally people did LPMs because it is very hard to do logistic regressions or logit or probit regressions. But now with computing power, it's very, very straightforward. So that's the reason we can actually focus on those two. It's just nice to know about LPMs, but focus on logit and probit models. So take a minute, let me think of any other ideas you have. Any ideas, that'll be great. Yes. So what do the equations look like? We know a normal regression looks like the usual one, right? Y equals beta naught plus beta 1 x1, beta 2 x2, all those kinds, plus of course the error. But in this, when you do an LPM, the Y can be either 0 or 1. I mean, it can be whatever, you just need a binary variable. So in the LPM, we have, when you learned about expectations, it's basically the expectation of Y given. Y given, remember the way it's written, Y given all these is nothing but the probability of that Y is 1 given all this, right? So not when Y is 0. That's what the linear probability models will do. Okay, and therefore the equation of Y is nothing but the probability that when Y is 1, that is the success, whatever it may be. So the beta coefficients, they are interpreted as a change in the probability that Y is equal to 1 holding constant the regressors. Okay, so think about it in that terms. Remember, so the 0 is failure, but we are looking at when it's a success. So this is a simple postulation of how the graph will look like. So our outcomes can be 0 and 1 only, right? And this is the actual data. The black dots are the actual data. Okay, so whatever has happened, you know, on various parameters, this is mortgage is approved, this is denied. And you can say success is denied, success is whatever, you know, it's up to you, it doesn't matter. So the actual data is binary. Now, when you're actually creating a line, your regression line may probably look like this blue line, but that makes absolutely no sense, because remember, we're talking probabilities. How can be probably more than 1 or less than 0? So therefore, these kind of traditional OLS will just not work at all. Okay, so we don't get the traditional OLS line, ordinary least squares. So that's the reason we use LPMs, so to overcome that. Now, when we actually get the data and we run the models, it'll be an S-shaped curve with the upper bounds as the 0 or the 1. So what is the interpretation? So let's take a simple one. A change in the X value by 1, similar to regression, is estimated to increase the probability that the Y value is increased or decreased by the beta value. So remember, if it's positive or negative. Okay, so remember, the focus is on the probability. So we've given an example here. A change in X by 1, whatever that X value is, right? Whatever that variable we talked about, is estimated to increase the probability that the Y value changes by 0.6. So it's the probability that we're actually sitting in. Okay. So I focus this a bit more. LPM produces predictive probabilities. Effect of delta, this triangle is basically delta. the effect of delta x is a change in conditional property that y equals 1. If you go back to the earlier one where we talked about the equation is nothing but when y equals 1, right? So similarly, here is what we're talking about. So if y is 0, 1 variable, then expectation of y given x is a proportion of 1's given x. Just like in the Bayesian method, you learned to put the Bayesian thing. That's very, very important, okay? So this is interpreted as a probability of y given x. So remember, this is the same as the expectation and the probability. But focus again on how LPMs do this. So let's take an example. Y equals 0.91 plus 0.008 times x plus u. Use your error. So what does this say? An additional year, let's say x is years, of x increases the probability of y by 0.8%. So it basically increases the probability of y, okay, by 0.8%. Remember, y can be 0 or 1. And how do you get 0.8? Basically converted that into a percentage. So be very careful of how you interpret this. Like I said, they're useful since it's easy to interpret the coefficients. They're also good to get started. You know, whenever you have a binary outcome, you should use this to get started. The economists love to use LPMs because the results are pretty close to logit or probit models, which are the ones we should use. Why? Because remember, we said those caveats with it. But we should only use probit and logit. So let's talk about probit and logit models. Like I said, you know, it's easier to do them now. Earlier econometricians did not use them because they were hard. The only difference here is that the interpretation of these are using odds ratio. So what is that? Nothing but the exponentiated value of the estimate. Okay, so it's an exponent, e raised to whatever. So whenever you get the beta values, let's say you run something, the beta value is 0.908. So then what you do is you sit down and just turn the exponent. So e raised to 0.098 is 2.47. Now, even if your beta value is negative, you're not going to get any e raised to negative numbers, also not a positive number. So this is what we call odds ratio. So when you're comparing those two, so let's talk a little bit more about this. Let's take an example. Suppose you want to check if the family, you have a family history of heart disease and what is the chance that you're getting a heart disease. If the odds ratio is 1, that means there is nothing. Family history has no association with CHD. If it's greater than 1, then there's a higher odds of family history present impacting coronary heart disease. That means if your family had a heart disease, if the answer for that odds ratio is greater than 1, that means it has a positive impact. And if it is less, then remember your beta will be negative, but there are lower odds. So basically, odds are just like we talk about what is the proportion, what is the chance happening. But the odds ratio is a ratio between the yes and the no, or the, let's say, whatever the binary outcome is, 0, 1, success, failure, male, female, whatever the outcome is, it's a proportion of those two. So whenever you're sitting and doing the odds ratio, you're basically thinking of, what is the ratio between the success and the failure? And that's how you actually interpret it. So that's what we are going to actually do today. So let's do a slightly different project here now. So using a data set from health, we will predict what factors could impact a coronary heart disease. Now this data is also from South Africa, and this is a South African heart disease actual data from about 400 odd people. Okay, so let's just get started on this particular thing. So what have we learned so far? What are LPMs? LPMs are primarily projects that you do with the outcome is a binary variable. And Normally LPMs are used, but the better way to use is logit or profit models, and that's what we're going to actually do. So in this, our outcome will be, did they get the CHD? And we're going to use variables to actually check that, okay? So let's just go back here, and I'm going to stop sharing right now. And we are going to go back and open R and actually run this. Okay, so I'm going to, you can pause for a few minutes, and we are going to actually sit down and open R and do that. While you're opening R, let me just, again, pause this for a few minutes. I would suggest pausing this for 2 or 3 minutes. I'm going to be quiet, and then you can actually open this. Okay, I hope you've had a few minutes to sit down and look at the open R and be ready. So here is R, and here is the data that you actually have. So here is the data of coronary heart disease. Now, when we got the data, we had from A through J. So CHD is nothing but coronary heart disease. And can you see C and no? C means yes, and no means 0. So I've just recoded that. I've just recoded the C to 1 and the no's to 0. Now look at the various factors. They've got tobacco, means are you smoking, your LDL levels, the adiposity, whether the family history, whether it's present or not, what kind of type A were you, obesity, alcohol, age. So you will probably have some kind of hypothesis about which causes CHD and which does not. So we're going to take this data set, and we're actually going to sit down and open R and start working on creating these things. So if you've opened R and you've got your data set ready, what you're going to do is go to R, and again, we're going to do R Commander, just so I want you to focus on understanding than the coding part. So library R Commander. And of course, you can actually sit and do the same thing code, and we'll show you the actual code too. You can take that. It's there in the PowerPoint as well, okay? So there's no hurry about that. So let's just wait. Let's just stop this for a minute while it's just loading up. And once it's ready, we will actually get started. So what are we predicting? What is the outcome? Why is it binary? Because you can either get the disease or you cannot get the disease. And we're looking at all these factors. Some of them are dummy, like family history, right? Family history, present or absent. And some of them are ratio, like your age is a ratio. The other ones that they had were also ratio data, okay? So we're going to actually sit down and look at both of these. Okay, so here we go now. Let's go here to our commander and go to data. import data, and you can of course do it in many different ways. So I'm not going to do this. And here, let's call the data set probit. No, let's call them logic models. Logic. You can call it anything. It's absolutely fine. They'll ask us to find the data, take the copy of, I say heart, open it. Now here is your first code. If you're doing it in RStudio, you can actually write this is your code. So now you've got the data. We saw what the data looks like, and now we're going to run this. In order to run this, what we're going to do is go to fit models, and we've already done linear regressions, and these are these other ones. We are going to do generalized linear model. Now, we had mentioned that logit is when you have two categorical outcomes. What happens if you have an outcome, but there are three, but they're still categorical? And so having binary, categorical, right? There could be situations where there could be three options, but they're still ordinal, they're still categorical. So in those situations, you'll do a multinomial. That means there are more than two. So this is the same, the situation remains the same, except that the outcome has more than two of these, okay? Then they have linear mixed models, ordinal regression, ordinal in case your DV is ordinal and you want to run it. General linear mixed model, and you can play around with this. But let's just go to GLM. So here, the model will, you can make your own, put your own model name, or we can just leave it default model. And here's the equation, just like we write the equation in normal regression and dummy interaction we showed you, here you can do it. So here, what are you trying to predict? So I want to predict coronary heart disease. So I do this, click on this, and double click. So that is this. And that is equal to what? So let's say I think, a lot of these factors will think, so I think age definitely. So I double click age, it comes here. Then I think it's a additive property, but so I put that. Alcohol, yeah, I think alcohol may also impact it. So we just do that, add it. We obviously have already got CHD. Let's do family history. Yeah. Oh, I forgot to the plus now. Now we can do obesity. People keep telling you if you're fat, you want this thing. How about tobacco? Okay. And you can put all of them, some of them. I'm just showing you how you can actually run this. Now, if you see these others, there's multiplicative, the division, there is exponents. You can actually use all of this. In case you want to do polynomial things, you can actually do that. You can change the degrees of polynomials. But for right now, we're just doing very simple things. But this has all those options. Here, they'll ask you whether you want to use all of them or you want to use some of them. And you say all of them. In weights, you have the option of do you want to weigh any one particular thing higher or lower. And right now, we don't want to because we don't know any theories behind it. Now here you have various probability distributions. Okay, so you can be Gaussian, binomial, Poisson, gamma, inverse Gaussian, quasi-binomial, quasi-Poisson. You've learned about basic binomial and Poisson in your basic statistics. Binomial means 2. So in our case, we have 2. So we are happy with that. So we're going to stick with that. But look at your underlying distribution, and then you can actually do that. By default, it does binomial. A link function, remember we said could be probit or logit, or they have an option of C log, but we are just going to go with logit. What is logit? Logit is nothing but logistic regression, we say. Probit is also something like that. The only difference is between logit and probit is whether your data is non-normal or normal, and also the link function, the actual math behind is slightly different. As far as you're concerned, let's just do logit for now, and let's see what happens. Let's see, okay. And There was some kind of error. So let's just run that. Can you see it's actually going to give the odds ratio too? So you can actually go down and look what the errors were here. One simple way to look at the errors is, let's just look at the error. It should give you an error issue right there at the end in red. And this is a good way to learn of, what's happening here. So we can actually sit down and let's look at this. And it says it's not found. So let's just run this again. And we do fit models. We do generalized linear models. GLM2. What happened? GLM1. Let's do yes. And then I'm going to do age plus alcohol plus family history plus, let's do obesity plus tobacco. And we have everything else looks okay. This is strange. We're going to stop right now. Okay, so let's go back, and we are in our R thing again, and we're going to go to statistics, fit models, GLM, and we've done coronary heart disease, alcohol, plus age, plus family history, and let's just say, okay. So now what we see is that this is actually sitting and giving us the output. Okay, so let's look at the output, and then let's just decide what we're going to do here. So I think there were some in the earlier thing, there was some, oh yeah, the outputs had come. I think we just didn't see it earlier. So let's just run this now. So if you have to write the code, you just write whatever the model name, and then the arrows, the GLM, the generalized linear model. This is your DV. This is your whatever IVs are, independent variables, your alcohol, age, family history. We've said it's going to be binomial and logit, and it's going to be logit. And here we'll give a summary. Very important to get the summary and the exponential coefficients. This is nothing that we call the odds ratio. So here is your code right here, right? I'm highlighting the code here, and we want this. This is your code. So if you use this in RStudio, that's all you have to do. I already have it in the PowerPoint. Make sure you put the summary and as well as thing. Now remember, GLM.5 is just the model name. So once you run this, you will get some basic statistics. This is your minimum, your maximum. So your minimum value is your residuals. Remember, so residuals can be negative. This is your first quartile, your median, and your fleet quartile. So you can see, the thing is more negative than the residuals are more negative than positive, the median here is. So now we come back. This looks exactly the same as our normal regressions. So here we have an intercept, estimates, standard errors, and the probability. As you can see, good news. If you love alcohol, this data set, not everything, only for this data set, we found that alcohol does not have a relationship. It's not significant for them. Age definitely does, and family history does. Now, if you look at both of these, which do you think has a higher impact? If you look at both these numbers, obviously family history. Now remember, they've written T present. That means when it's present. It's absent or present. So this is when we're talking about when it's actually present. If you've forgotten this particular the p-values, you can actually look at the stars. If they're stars, it's significant, and obviously this is not. If you go down a little bit, you can actually look at the A1C number, okay, the AIC number, which actually tells you how good or bad the model is, which again you've learned in other projects. We're not going to focus on this. And here is our exponent or the odds ratio. So in here, can you see the odds ratio for alcohol and age and family history all above 1? But just like we saw earlier, the family history is the highest beta value. Here, the family history is just give us the highest value here, 2.528. So how did they get this? They basically took this number, did exponent of 0.927, and you will actually get these numbers. So now alcohol and age. Now remember, we said if the odds ratio is 1, that means there's really no association. So it says how old you are or whether you consume alcohol. For this data set only, we find that there is no impact on CHD. But a family history, definitely, right? If it's present, you have 2.5 times more chance. We have 2.5 times more chance of getting CHD than not. Okay, let's try another one. Okay, so let's go back and you can try some more. You can add more things in that. Let's add, what else should we add? We've got age, we've got alcohol. Let's do tobacco. And let's see if tobacco works. So same thing first, let's go up and check whether there is, no, tobacco is significant, but it's of course lower than family history. But if you notice, between tobacco and age, tobacco has a higher level than age, right? So if you're drinking, smoking, then it has. So now look at this. Again, family history is the most. Alcohol actually gone down, but we don't care because it doesn't help. Because age is almost 1 and tobacco is slightly above 1. So this is what we would call a logit model, which is a better thing than linear probability models, but that's the actual focus. So I'm going to repeat these again so you get a good example, and you can pause this slowly and run this. I'm going to do this very slowly. You got your data, go to fit models, go to generalized linear models, and you can now add any other things as well. Let's try, what else would you like to try? Try obesity. Anything else would you like to try? And you can play around and try your own things. Maybe we can remove alcohol because alcohol seems to have no impact at all. Would you like to do type A? Or this is good enough, right? So just say okay. And let's see what is happening here. Go back and look at the numbers which are significant. Okay, obesity is not significant. Obesity does not matter. So next time somebody says, hey, you're fat, you'll get a heart disease, you're like, oh. Now this is only in the South African data. We don't know what data works for you all, okay? But family history seems to have an override. Okay. So I just wanted to show you the other one, which we're obviously not covering today, but this is multinomial. In this, what happens is the outcome is not binary, but more than 2. Similar kind of situation, you work it exactly the same way. And here, of course, if you need help, you can actually get some help in your model formula. We're just going to close that. So again, LPMs are linear probability models. You can actually sit down and look. It's ordinal, I said we talk about. Similar way. And here you can have the proportional odds logit or an ordered probability. Same thing that we talked about earlier too. Okay. Let's look at the other one. And there is your linear mixed model. As you can see, you have different methods. You've probably read about the maximum likelihood or the restricted maximum likelihood. If you have, great. Otherwise, don't worry about it. If you have a mixed model, you can actually use this. And let's say okay. And here we go to the last one, which is generalized linear, which is Again, the same thing, but you have all these other options as well. So as you can see, our command has a lot of options for you. You can sit down and use them and work with things as well, right? You can also do your effect plots and predictor effect plots. You can do all of those right here. Let's go back to our presentation and finish that off. So as we saw, the data is the one that can actually use from, again, the Google Drive that you can have. Here, I have just written some of the code, but of course, you've also seen it there. And if you have, say, a variable y, which is yes and no, and you want to change it, this is a simple R code that you can write for that. So what did we learn today? We've learned that binary dependent variables can be used in regression using LPMs. Last time when we did dummy variables, we said, hey, we can use binary dummy variables. I mean, we can use categorical independent variables as dummy variables. But this is what happens if it is in the outcome. The interpretation is in probabilities and odds ratio for logit and probit models. And please, please, please try and use logit and probit models. Even though LPMs are easier to interpret, this is a much, much better powerful use. I hope this is useful and good luck with your studies. Have a wonderful day, and it was wonderful talking to you